Hello, I'm Mr. McChesney, and today we're talking about image position and image height. So we have a problem here where a concave mirror has a radius of 20.0 centimeters and a 2.0 centimeter tall object is 30.0 centimeters from the mirror. What is the image position and image height? So when you're doing this, you want to make a couple of drawings. So we have our object here, and there are a couple of rays you can draw in. You can draw a ray in that goes parallel to what's called the principal axis, which is basically where the center of the mirror is, or the bottom of your object is. And that ray goes in parallel, hits the surface of the mirror. In this case, because we have a curved mirror, we usually draw a line that's tangent to the center of the mirror. And that line reflects and goes through the focal point. The second principal ray you'll draw in goes through the focal point, hits the mirror, and comes out parallel to the principal axis. So if you go in parallel, you hit the focal point coming out, and if you go in hitting the focal point, you'll come out parallel. And the spot where those rays intersect is where your image is going to form. So in this case, our image is forming in front of the mirror, and it's upside down. So since these rays converge, that means we've got a real image, something that we could project on a screen. So this would be type of image that'd be used when you go to like the movie theater. And there's one more ray you can draw, which I'll show you here to kind of double check your work, is if you go from the image, or the object through the curvature, the center of curvature of the mirror, all the way down to the mirror, it comes straight back up, and if you did everything right, all three rays should hit the same point. And then you just draw in your image going from the principal axis down to where it was. And once you've got these three rays drawn in, every other ray that strikes the mirror, so if I have a ray that's going to come along in some other way, it's going to strike the mirror, the light has to go through that spot. So we use those three principal rays to show us where our image is. And then we can draw the other ones in if we need to. So now you've got a drawing, we now have to list all our known information. So for instance, we start with the height of our object, and we look in our problem that said it was 2.0 centimeters tall. We have the distance of our object from the mirror, and that's 30.0 centimeters. And lastly, we have the curvature, or the radius of curvature, how much the mirror curves, which was 20.0 centimeters. So all of our numbers have the same units, so we don't have to do any conversions in that. And then it asked us, what were we looking for? Well, we want to know what's the image position, how far is the image from the mirror, which would be the distance. And then we also want to know how big is the image, the height of the image. So now we have all our unknowns and knowns. So the first thing we have to do is figure out what's our focal point, or how far away is this focal point. So that's pretty easy to figure out. If we go with our equation for this, our focal length is going to be half of the radius of curvature. So that's pretty simple. We had 20.0 centimeters for our radius of curvature. And we're just dividing it by 2. And that's going to give us a focal length of 10 centimeters. Alright, so now we've done the focal point, which is something we need when we go and solve for the image position. So if we look back in the chapter, we'll see the formula you use, which is 1 over your focal point equal to 1 over the distance to your image plus 1 over the distance to your object. Now in order to get the version of the equation we want, where we solve for this, we have to do some algebra. So let's look at that algebra. So the algebra we got to do is we want to make this side of the equation have common denominators. So in order to do that, we're going to get one over f still, and when we multiply both parts of the fractions to get a common denominator, we're going to end up with distance of the object plus distance of the image over their most common denominator, which is di times do. The next step, then, we want to get rid of these fractions. So I'm going to take and multiply both sides by f to get rid of the f, the focal point. When I do that, I'm going to get f divided by f, which is equal to 1. And we'll get do plus di over di times do, and all of that will be multiplied by f. Then I want to get rid of my part here, the di times do, so I'm going to multiply both sides by di and do. And I really should give myself more room to work here, but sometimes you don't. So that cancels that out because it's on the top and the bottom of the fraction. So now I'm almost where I need to be. I got di times do, and that's equal to my focal point times the quantity do plus di. Alright, we're almost done now, but now I need to get di by itself, so I'm going to pull di out, and when I do all the algebra you need to do, and you'll notice in the sample problem we just kind of gloss over this step. So here's a little extra work so you can amaze your physics teacher that you did all this, and they'll say, wow, you went the extra mile. So we get the final answer of the focal length times the distance to the object divided by distance of the object minus the focal length. So if you look in the sample problem, that's the form of the formula you see that we're going to use. So now let's plug in that information. 10 centimeters is my focal length. And as always, use your units. And I'm going to multiply that times the distance to my object, which was 30 centimeters. And then I divide it by my distance to my object, 30 centimeters, minus my focal point, 10 centimeters. Alright, so we're almost done with this part of the problem. We find out that the distance of the image is equal to 15 centimeters, 15.0 centimeters. And we find that we have a real image and it's in front of the mirror. If we look at our diagram, we can see that here's our object, here's our image. It does look like it's about halfway in between. Our curvature of the radius was 20 centimeters. Our focal point was 10 centimeters, and it looks like we drew it so it's right halfway in between those two, which would be 15 centimeters. So that should mean that the work we did in both our drawing and our formulas worked out to give us the true image. So now we have to answer the last question, which was, how big is this image? So you want to use the magnification equation to solve for the image height. So back in the book, it says that M is equal to HI over HO. And that is equal to the opposite, or the negative, of the distance to the image divided by the distance to the object. So if we rearrange this part of the equation, we can solve for what we want. So I'm going to take and multiply the height of the object on both sides of the equation. So I'm going to end up with the image height is equal to negative the distance image times the height of the object divided by the distance to the object. So if we plug our numbers in, height of our image is equal to a negative sign. Don't lose track of that. It's important. 15.0 centimeters times the height of our object, 2 centimeters, divided by the distance to our object, 30 centimeters. So when we do all that math, we get negative 1.0 centimeters. Because we had 15 times 2 is 30, and 30 divided by 30 is 1, and we had a negative sign. So if we look back at our image, that's saying when we look at this, if this is 2 centimeters tall, this should be about half its height. And that looks about right. So that means that also we've done that correctly. So we should see a smaller image that's upside down. And when you project a real image onto the screen, it always flips it upside down.